Almost everything in your life today, your phone, your car, and many of the technology shaping the future depends on the piece of technology most of us never see the advanced shape. Hello everyone, I'm Ashisatika Muslim and I want to challenge how we protect it. My argument is resilience shouldn't mean rebuilding the entire supply chain from scratch. It means a smarter choke point specific approach that targets the real vulnerabilities, weighs every trade-off and verifies whether the risk actually falls. Let's talk through 5 stages together. Think of it as building a house from the ground up. A semiconductor is the foundation, a material whose conductivity we can control. A transistor is a tiny switch built on it, where enough transistor together and you can get integrated circuit, package it, and you have a chip. Here, advanced chip means leading edge fabrication, architecture, or packaging. And here's something surprising: node level like 3 nanometer don't measure it. They name a whole generation of technology as TSMC shift from M3 to M2 shows. So why should you care? Current 2 nanometer class production is concentrated among TSMC, Samsung, and Intel. Advanced chips support AI accelerators, data centers, high performance computing, and self driving systems shaping our future. Under SDGs 9.5, which focuses on strengthening specific scientific research and technological capability, this creates a genuine development opportunity, stronger research capacity, and higher value industry. But here's the catch. Under SDG 9.4 and 12.2, that upgrading is only sustainable if production also becomes cleaner and more resource efficient. Keep that in mind. I will return to this tension in slide 5 and 7. Picture the semiconductor supply chain as a relay race across the globe. Design and IP starts largely with US federal firms, companies that design chips, outsource manufacturing. The pattern then passes to specialized supplier in the Netherlands. SML makes extreme ultraviolet or UV lithography system used for leading edge production. While Japan is important for chemical and silicon wafers, much of leading edge fabrication remains concentrated in Taiwan and South Korea. Packaging and testing then extended across Taiwan, Malaysia, Vietnam, and Philippines. This creates a network of choking. The problem is not that one country controls everything, but that different stages dependent on highly specialized capabilities. A broad disruption such as COVID-19 can affect the whole network, but a choke point is different, restricting area access to a hard substitute technology such as UV can constrain leading edge production even when other parts of supply chain are available. This is where the sustainability trade off becomes visible. I focus on the diversification emission relationship because the evidence is the strongest here. TSMC expanding leading edge production in Arizona, including 4 nanometer, 3 nanometer, and planned 2 nanometer, and the beyond capacity partly to increase geographic flexibility. But capacity expansion also creates environmental pressure. TSMC report that its 2024 greenhouse gas intensity was 19% above its 2020 baseline, even though its target was 10% below that baseline. This is production normalized measured, so it refers to emissions per unit of production rather than total emission. TSMC linked the missed target partly to advanced process growth, insufficient reduction measure, and limited renewable energy. Importantly, the report doesn't identify which site caused the increases. So, my conclusion is careful diversification can reduce geographic risks, but advanced capacity growth can also increase emission pressure unless low carbon energy and mitigation are built in from the start. So, what's the policy response? Not full self sufficiency, that would be costly, be unnecessary. My proposal is targeted redundancy around a specific choke point, advanced fabrication. First, governments can co fund limited alternative capacity since a state of the art advanced fab can require up to about 20 billion US dollar in capital expenditure. Second, support should cover the ecosystem around it, skills, research, reliable electricity and water, not just the fab itself. Third, public support should carry a resilience condition. New capacity must demonstrably reduce dependence on the original hub while remaining globally connected for equipment, material, and design tools. My test is simple. Does this investment actually reduce the consequences of losing the original hub? Slide 5 showed that the advanced process growth can increase its emission pressure inside a fab. That pressure comes from hundreds of repeated manufacturing steps. A wafer can pass through 400 to 1400 depending on complexity. My technology responses focus on two levers: abating process gases at the source and improving tools energy efficiency. TSMC reports a 96% FGAG reduction rate and 810 gigawatt hours of electricity conserved in 2024. I would track progress using production normalized indicators, greenhouse gas emission, and energy per wafer equivalent mass layer. But there is a scale limitation. Even if each wafer becomes cleaner, total emission can still rise if capacity grows faster than efficiency improves. So, how do we decide? Choke point by choke point, I propose 5 steps. Diagnose. Where do concentration and low substitutability create a genuine choke point? Justify. Would invention materially reduce the consequences of disruption? Match. Choose the responses that fits the choke point, selective capacity for fabrication, but secure access rather than duplication of UV. Stress test. What new vulnerability could this response create or shift elsewhere? Finally, verify. Did vulnerability actually fall? And were the resulting trade-offs acceptable? One principle ties that the framework together, reduce the choke point without simply moving the risks elsewhere. Three things to take away. First, fragility comes from concentrated hard to substitute choke point, not simply a shortage of capacity. Second, government should respond selectively, matching the intervention to the choke point rather than the pursuing full self-sufficiency. Third, every resilience measure needs to be stress tested so that solving one vulnerability doesn't create another, particularly environmental pressure from added capacity. This matters because resilience should be judged by whether vulnerability falls without creating an unacceptable sustainability burden. My view in one line, resilience means reducing dependency without relocating risk. I would judge success using three indicators: lower concentration, faster recovery, and lower production normalized emissions intensity. The full references supporting this presentation are listed in this slide. Thank you very much for your attention, and I hope this presentation has shown why semiconductor resilience must be strengthened without simply shifting risks elsewhere.